We're going to talk about scatterplots, association, and correlation. So a scatterplot is just a graph that is a bunch of dots. Those dots are X and Y ordered pairs, just like we saw in algebra or anything like that that you took. We plot the X along the horizontal axis, and we plot the Y coordinate along the vertical axis. So each individual dot that's here represents one data point in my scatter plot. So this is years since 1900 on the horizontal axis, and percent of people responding yes on the vertical axis to whatever our question was. It doesn't even matter. So let's say that I want to interpret this data point that's right here. So notice this is about what? Maybe let's call that 48 on the axis here. So that's 48 years after 1900. So in 1948, what happened? Okay, let's look over here, and that's maybe about 47. So we would say 47% of respondents said yes, right? That's how I'm reading that individual data point. So I can read each one of these data points that same way. So I am most interested, for the purposes of this course, we're most interested in relationships that look like a line. So this scatter plot, notice, has a general upward trend to it. So it kind of has like an upward line to it. Notice this doesn't look exactly like a line, right? There's lots of points that are nowhere near this line that we see there, okay? But something that has a general upward trend to it has a positive linear correlation. These have a general downward trend. So this is a negative correlation. These are all over the place. So there's no correlation here. Now, I can also have a figure that does not look like a linear correlation, but maybe some other kind of shape. So if I have a scatter plot that looks something like this, unlike this one, which is no correlation, this is not just random all over the place. I see a little bit of a pattern there. And that pattern might look like another curve, like say in this case, a parabola from college algebra. So this would just be not linear, right? We might have another type of correlation there, but it's not a linear correlation. Linear correlation specifically means we're fitting a line to it. So this is fitted with an upwards line, hence a positive correlation. This one is fitted with a downward sloping line, hence a negative correlation. So the explanatory variable is plotted on the x-axis, and the response variable is plotted on the y-axis. We believe that the explanatory variable partially explains the value of the response variable. For example, people with higher incomes people with higher education levels generally have higher incomes. So my explanatory variable here is the education level, and the response variable is the income level. Now notice that this is not a causal relationship. In other words, having a higher education does not cause you to earn more money. I know many people with advanced degrees who are unemployed. I also know many people who don't even have a high school degree who are earning 6 figures a year. It's not causal, but usually it is the case that higher your education level is, or people with higher education levels tend to be in the higher income brackets. So a correlation exists between two variables when one is related to the other. We measure the strength of that relationship with R. This lowercase r is the linear correlation coefficient. R squared is the proportion of variation in Y that is explained by the relationship between the two variables. Now that linear correlation coefficient is a value that runs between -1 and +1. The closer it is to -1, the stronger of a negative correlation there is. The closer it is to positive 1, the closer it is to a positive correlation. Right in between the two, the closer it is to 0, no correlation exists between. Okay, so in other words, if I have an R value that's close to 0, I have a very, very weak correlation between the two variables. There's not much of a relationship between them. If I have an R that's close to positive 1, then there's a very strong positive correlation. Now look at what happens with a positive correlation. When the X increases, the Y also increases. Right? They both go up at the same time. When I'm close to negative 1, it's a strong negative correlation. When the X increases, the Y decreases. That's a negative. Okay? So now, my conditions for correlation. I've got to be dealing with two sets of variables that are just numbers. They need to look somewhat like a line, and there can't be a whole lot of outliers. If there are outliers, we need to look at the data with and without the outliers and investigate. Let's look at an example. Let's look at number 40 on page 169 of our textbook. So going over to our textbook here, I'm looking at number 40 here. I want to look at the association between fat and calories in a fast food hamburger. So the first thing that I'm going to do is I'm going to go over to my calculator. I'm going to hit just hit the stats key and go into the edit menu and enter the fat in L1 and the calories in L2. I've already done that, so you can pause the video here and go ahead and enter that yourself. But in general, we put the explanatory variable in L1 and the response variable in L2. I believe that fat tends to explain the calorie content, usually not the other way around, right? That's a more natural association. Now, if I hit second and the y equals key, I'm going to turn my first plot on. So I want to make sure that says on, and then go down here to the scatter plot. And I want the X list to be list 1 and the Y list to be list 2, since I arranged it that way. And then I am going to go to Zoom 9, the Zoom stat menu. And there's my scatter plot, and I can see that there is a positive linear association between the two variables. Okay? So, this tells me not only is there a general trend that as the fat content increases, the calorie content also goes up, but I also see one value over here that's kind of off to the side a little bit. Okay, that may be influencing my relationship a little bit here. But let's go ahead and take a look at it first. So we're going to go to the stat key and over to the calc, and option 4 is my linear regression there. And we're going to talk more about that in the next video. But I want it to be list 1 in the X, list 2 in the Y, and then go down to my calculate. And notice, I forgot to turn on my diagnostics. All right, so I'm going to show you how to do this. You only need to do this one time. If I go to second and catalog, and then down to the D's, and see where it says diagnostic on, this will show you the value of R. You don't need to turn it on again. Once you turn it on one time, you don't need to turn it on again unless you like reset your calculator. Then you'll need to turn it back on, okay? Otherwise, once you turn it on, it'll stay on. So just hit diagnostic on, it'll say done. Now when I go to stat, calc, option 4, it's going to show me the R. My R is 0.96, and that's a strong linear correlation. Now, if we run it again without the outlier, we'll see that that correlation goes down a little bit. that R should go down to about 0.83. Try deleting that outlying point and see if you get a correlation of 0.837.